Welcome! Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's most dangerous birthday gift, the breath that nearly killed everything. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The Earth spins in purple twilight, 2.5 billion years before the first human breath. Its atmosphere tastes of methane and hydrogen sulfide, the chemistry of swamps and decay stretched across an entire world. No oxygen moves through this ancient air. The sky holds a different promise, painted in shades of salmon and rust, while continents drift like dark islands through seas that shimmer with an alien iridescence. In these primordial oceans, bacteria paint the water purple-red with their rhodopsin pigments, harvesting sunlight without splitting water molecules, without releasing the gas that will one day fill human lungs. They are anaerobic organisms, perfectly adapted to a world without breath, thriving in the chemistry that would poison modern life within minutes. Their purple mats stretch across shallow seas, photosynthetic carpets that know nothing of the revolution brewing in their microscopic depths. The iron in these ancient waters remains dissolved, unoxidized, giving the oceans a greenish transparency that modern seas will never possess again. This is the signature of a reducing atmosphere, a world where electrons flow freely, where metals stay in solution, where the chemistry runs backward from everything familiar. Only volcanic gases and the slow escape of hydrogen to space disturb the atmospheric equilibrium that has persisted for nearly 2 billion years. Continents in this ancient world exist as scattered fragments, dark volcanic islands rising from purple seas. No soil clothes their surfaces, only bare rock and mineral crusts baked by ultraviolet radiation that penetrates the ozone-free atmosphere without mercy. Rivers carry dissolved metals in concentrations that would be toxic to any modern organism, painting mineral deposits in patterns that will puzzle geologists billions of years in the future. The land waits, sterile and patient, for life that can survive the coming transformation. How quietly it all proceeds, this purple planet in its methane greenhouse. Maintaining temperatures warm enough for liquid water, despite receiving 25% less solar energy than today, the reduced sun burns cooler. But Earth compensates with its blanket of greenhouse gases, methane trapping heat with an efficiency that carbon dioxide can barely match. This delicate balance has persisted for 2 billion years, a planetary thermostat that will soon be destroyed by the very life it nurtures. The atmosphere holds mysteries that modern chemistry struggles to explain. How did methane concentrations remain so high for so long without biological production? Volcanic outgassing provides some answers, but the precise mechanisms remain obscured by deep time. Perhaps serpentinization reactions at mid-ocean ridges contributed more methane than current models suggest. Perhaps the early mantle held more reducing power than geochemists have calculated. The purple world keeps its secrets buried in rocks that have been metamorphosed beyond easy reading. Beneath the purple bacterial mats, other organisms pursue stranger chemistries. Sulfate-reducing bacteria process the dissolved minerals in ancient seawater, creating hydrogen sulfide that bubbles to the surface in quantities that would asphyxiate modern ecosystems. Methanogenic archaea ferment organic matter into methane, maintaining the greenhouse that keeps this world warm. All of them live without oxygen, extracting energy from chemical pathways that modern life has largely abandoned. Only took 2 billion years to perfect this chemistry. Only took evolution eons to develop organisms so perfectly adapted to a reducing world that they would find oxygen as toxic as cyanide. Only took the slow accumulation of biological innovation to create ecosystems of stunning complexity, all based on the chemistry of electron donation, of reduction reactions, of metabolisms that would seem alien to oxygen-breathing life deep in the primordial seas. Evolution experiments with new forms of photosynthesis, unaware that it is about to invent the most successful poison in planetary history. Some bacterial lineages begin developing photosystem complexes that can harvest light energy from shorter wavelengths, accessing solar radiation that their purple predecessors cannot use. They learned to split hydrogen sulfide instead of organic molecules, a small step toward the catastrophe of water-splitting photosynthesis. The purple world drifts onward through space, its methane atmosphere refracting sunlight into orange and salmon hues that no human eye will ever witness. Tidal forces from a closer moon churn the purple seas more vigorously than modern oceans, mixing nutrients and bacteria in patterns that drive biological productivity to levels that will never be equaled again. The ancient Earth spins faster 2 days, lasting perhaps 18 hours, accelerating the rhythm of tides and weather in a world where weather means methane precipitation and sulfur snow. This is the world that oxygen will destroy not through violence, but through the patient chemistry of molecular transformation. Every breath that will ever be drawn depends on the annihilation of this purple paradise, on the death of ecosystems that flourished for longer than complex life has existed. The ancient bacteria know nothing of their coming extinction. They photosynthesize and reproduce and evolve in their reducing seas, following chemical gradients that lead them toward the most successful evolutionary innovation in planetary history and toward the near extinction of everything they represent. The purple Earth breathes its ancient atmosphere of methane and sulfur, while microscopic revolutionaries prepare their assault on everything familiar, everything perfect, everything that has worked for 2 billion years of planetary time. In the bacterial mats that carpet ancient seafloors, evolution stumbles upon a discovery that will transform worlds. Among the purple sulfur bacteria and the green filamentous organisms that have dominated photosynthesis for eons, new lineages emerge with a dangerous innovation. They are cyanobacteria, blue-green in coloration, unremarkable in size, catastrophic in their metabolic ambitions. They learn to split water molecules, extracting hydrogen atoms for photosynthesis and discarding oxygen as biological waste. The innovation appears gradual, almost accidental. Some ancestral bacterial lineage develops photosystem 2, a molecular complex capable of harvesting light energy powerful enough to tear electrons from water molecules. This represents a quantum leap in biological chemistry, literally. The energy required to split water exceeds anything that earlier photosynthetic organisms could generate. Previous bacteria extracted electrons from hydrogen sulfide, from organic molecules, from reduced iron compounds. Water splitting requires photons of higher energy, more sophisticated molecular machinery, more complex cellular architecture. Cyanobacteria begin as minority players in ancient microbial ecosystems, their oxygen production initially negligible compared to the vast reducing power of the primordial atmosphere. Volcanic gases, hydrogen escape to space, and countless anaerobic organisms maintain the chemistry that has defined Earth for 2 billion years. The first oxygen molecules released by these primitive cyanobacteria react immediately with dissolved iron, with sulfur compounds, with organic matter floating in ancient seas. No free oxygen accumulates. The ocean chemistry absorbs this poison as quickly as life produces it. Yet the innovation spreads through bacterial populations with the inexorable patience of evolutionary advantage. Cyanobacteria can photosynthesize in environments too poor in reduced compounds to support purple sulfur bacteria. They can harvest sunlight in deeper waters where hydrogen sulfide concentrations drop too low for traditional photosynthesis. They thrive in conditions that would starve their anaerobic competitors, slowly expanding their populations across ancient seafloors. The molecular machinery they develop will persist unchanged for billions of years. Photosystem 2. The water-splitting complex that cyanobacteria evolve in these ancient seas will eventually power every plant on Earth. Chloroplasts. The organelles that enable modern photosynthesis are domesticated cyanobacteria, still carrying the genetic sequences and protein structures developed in this primordial world. The enzyme rubisco, which will become the most abundant protein on Earth, begins its career in these early cyanobacterial cells. Scientists studying modern cyanobacteria find molecular fossils of this ancient innovation. The oxygen-evolving complex contains manganese and calcium atoms arranged in precise geometric clusters, suggesting that early cyanobacteria evolved in manganese-rich environments that no longer exist on Earth's surface. The protein sequences retain signatures of adaptation to high-temperature conditions, indicating that the ancestors of modern cyanobacteria lived in hydrothermal environments or shallow seas heated by a more active young sun. Only took evolution hundreds of millions of years to perfect this molecular machinery. Only took natural selection countless generations to develop organisms capable of performing the most thermodynamically demanding reaction in biology. Only took the patient accumulation of genetic innovations to create bacteria that could extract energy from the most abundant molecule on planetary surfaces, water itself. But the mystery deepens when scientists examine the distribution of early cyanobacterial fossils. They appear simultaneously in rock formations across multiple continents, suggesting either rapid global dispersal or multiple independent origins of oxygenic photosynthesis. How did this complex metabolic innovation arise so quickly in geological terms? Did horizontal gene transfer accelerate the spread of photosystem 2 between bacterial populations? Did environmental pressures favor water-splitting photosynthesis simultaneously in different oceanic basins? The ancient seas begin to change color as cyanobacterial populations expand. Purple bacterial mats acquire blue-green patches where cyanobacteria establish themselves in ecological niches that traditional photosynthetic organisms cannot exploit. The ocean chemistry remains overwhelmingly reducing, but microscopic oxygen bubbles begin rising through water columns for the first time in planetary history. Most react with dissolved iron before reaching the surface, but some escape into the atmosphere, where they encounter ultraviolet radiation that splits them into highly reactive atomic oxygen. Cyanobacteria develop in filamentous chains, in colonial mats, in structures called stromatolites that will become some of Earth's most persistent biological formations. They build layered mineral deposits as they photosynthesize, trapping sediments between bacterial films and creating dome-shaped structures that can grow for thousands of years. These stromatolites become the first large-scale biological constructions on Earth, visible from space, altering coastal environments through their sheer abundance. The bacteria themselves remain microscopic, but their collective impact begins to register in global geochemical cycles. They produce oxygen at rates that seem insignificant by modern standards, perhaps 1/10,000th of contemporary photosynthetic output, but this represents the first sustained oxygen production in planetary history. The ancient Earth has never experienced biological oxygen generation. Its chemistry has no mechanisms for managing this new molecular poison. Cyanobacteria photosynthesize with the mechanical persistence that will characterize life for the next 2.5 billion years, splitting water molecules and releasing oxygen into seas that have never tasted this corrosive gas, building populations that will eventually challenge the atmospheric chemistry of entire worlds. Oxygen molecules rise through primordial waters like tiny molecular bombs, each one seeking chemical targets in an ocean that has never known such violence. They emerge from cyanobacterial cells as waste products, unwanted byproducts of water-splitting photosynthesis, but they carry enough reactive energy to transform everything they touch. The ancient seas respond to this invasion with chemical defenses that have been building for 2 billion years: dissolved iron, sulfur compounds, and organic matter that can neutralize oxygen before it spreads too far from its bacterial sources. The iron-rich oceans of the Archean world contain concentrations of dissolved ferrous iron that modern seas cannot sustain. These ancient waters hold iron levels hundreds of times higher than contemporary oceans, creating a reducing environment so powerful that it can absorb massive quantities of oxygen without accumulating any free gas in the water column. When oxygen molecules encounter dissolved iron, they bind immediately, forming ferric iron compounds that precipitate out of solution as rust-colored minerals. This precipitation creates the first signs of the coming transformation. On ancient sea floors, thin layers of iron oxide begin accumulating wherever cyanobacterial populations photosynthesize in significant numbers. The deposits appear as red and orange stains on otherwise gray sediments, chemical signatures of oxygen production that will persist in rock formations for billions of years. Geologists studying these ancient deposits find evidence of seasonal variations in oxygen production, suggesting that even primitive cyanobacteria follow daily and yearly cycles of photosynthetic activity. The chemical reactions proceed with mathematical precision. Each molecule of oxygen combines with 4 atoms of dissolved iron, creating iron oxide minerals that settle through the water column like microscopic snow. The process requires enormous quantities of iron to neutralize even modest amounts of oxygen production. Scientists calculate that the ancient oceans contained enough dissolved iron to absorb oxygen for tens of millions of years before free gas could begin accumulating in seawater. But cyanobacteria reproduce and spread across ocean basins with biological persistence that overwhelms even the iron-rich chemistry of ancient seas. Their populations double and redouble, establishing colonies in shallow waters where sunlight penetrates most effectively, building stromatolite reefs that become centers of intense oxygen production. The molecular waste from their photosynthesis begins to exceed the neutralizing capacity of local iron concentrations, creating the first pockets of oxygenated seawater in planetary history. These oxygen-rich zones expand slowly, creating underwater deserts where anaerobic organisms cannot survive. The dissolved oxygen concentrations remain far below levels that modern marine life requires, but they represent concentrations high enough to poison bacteria that have evolved in reducing environments for billions of years. Anaerobic organisms flee from these toxic zones, retreating to deeper waters where iron concentrations remain high enough to neutralize the oxygen threat. The ancient atmosphere begins to register traces of this underwater revolution. Oxygen molecules that escape from surface waters encounter an atmosphere composed primarily of nitrogen, methane, and carbon dioxide, with trace amounts of hydrogen sulfide and ammonia. The first free oxygen molecules in Earth's atmosphere react immediately with methane, creating water vapor and carbon dioxide through combustion reactions that occur spontaneously at the molecular level. Scientists studying ice cores from Antarctica find no direct evidence of this ancient atmospheric transformation. The ice record extends back only hundreds of thousands of years, but they can model the chemical reactions that must have occurred when oxygen first encountered the methane-rich atmosphere of the Archean world. The reactions generate heat, water vapor, and carbon dioxide, fundamentally altering the greenhouse properties of the atmosphere in ways that will drive climate change on a planetary scale. Only took a few million years for oxygen production to overwhelm the ion absorption capacity of entire ocean basins. Only took cyanobacterial populations a geological instant to begin transforming seawater chemistry that had remained stable for 2 billion years. Only took evolution this brief moment to invent a waste product so toxic that it would nearly sterilize the planet that created it. The mystery of early oxygen distribution puzzles atmospheric scientists who study the transition from anaerobic to aerobic Earth. Computer models suggest that oxygen should have accumulated uniformly across ocean basins, but geological evidence indicates highly variable oxygen concentrations in different marine environments. Perhaps ocean circulation patterns in the Archean world differed dramatically from modern currents. Perhaps biological oxygen consumption by anaerobic organisms created local sinks that prevented uniform distribution. Volcanic islands in ancient seas become the first landscapes to experience atmospheric oxygen. The gas molecules that escape from surrounding waters encounter subaerial environments where no biological or chemical mechanisms exist to neutralize them. These island surfaces begin experiencing oxidation, weathering for the first time in planetary history, as oxygen reacts with iron-bearing minerals in volcanic rocks, creating rust-colored soils that will become characteristic of oxygenated worlds. The ocean chemistry fluctuates between reducing and oxidizing conditions as cyanobacterial populations wax and wane in response to environmental changes. Seasonal variations in sunlight, nutrients, and water temperature drive cycles of oxygen production that create alternating layers of oxidized and reduced minerals on ancient seafloors. These chemical oscillations will eventually stabilize into the banded iron formations that become some of Earth's most distinctive geological features. Oxygen bubbles rise through primordial waters with the persistence of molecular time bombs, each one carrying enough chemical energy to poison anaerobic life, to rust dissolved iron, to begin the slow transformation that will make this ancient world unrecognizable to the organisms that created it. The first breath becomes poison as oxygen accumulates in concentrations that overwhelm the chemical defenses of ancient life. What began as molecular waste from cyanobacterial photosynthesis transforms into the most successful toxin in planetary history, a corrosive gas that attacks the cellular machinery of organisms that have thrived in reducing environments for 2 billion years. Oxygen molecules penetrate bacterial cell walls and react with sulfur-containing proteins, with iron-sulfur clusters that enable electron transport, with lipid membranes that maintain cellular integrity. For anaerobic organisms, oxygen represents molecular chaos. Their enzymes have evolved in environments where electrons flow freely, where reducing conditions maintain the delicate chemistry of life. Oxygen strips electrons from organic molecules with a violence that disrupts every aspect of cellular metabolism. It oxidizes the iron atoms in cytochromes, destroys the sulfur bridges that stabilize protein structures, generates reactive oxygen species that tear apart DNA and RNA with indiscriminate chemical aggression. The kill mechanisms operate at the molecular level with precision that no biological toxin can match. Oxygen reacts with superoxide dismutase, an enzyme that anaerobic bacteria never needed to evolve because they never encountered the superoxide radicals that oxygen metabolism produces. It generates hydroxyl radicals that attack cellular membranes, creating lipid peroxides that propagate chain reactions of molecular destruction. It oxidizes the reduced sulfur compounds that many anaerobic bacteria use for energy, eliminating their food sources while simultaneously poisoning their metabolic pathways. Ancient bacterial populations begin dying in massive numbers as oxygen concentrations exceed the buffering capacity of iron-rich seawater. The extinction proceeds with the slow inexorability of chemical warfare, killing organisms not through predation or competition, but through the fundamental incompatibility between their cellular chemistry and the new atmospheric conditions. Entire lineages of bacteria that dominated marine ecosystems for hundreds of millions of years vanish from the fossil record within relatively brief geological intervals. The dying creates chemical signatures that persist in rock formations for billions of years. As anaerobic bacteria decompose in oxygenated seawater, they release organic compounds that react with dissolved minerals to form distinctive carbon isotope ratios. Geochemists studying ancient rocks find evidence of massive bacterial mortality in sediments deposited during the early phases of atmospheric oxygenation. The carbon isotope signatures suggest population crashes of unprecedented magnitude in the history of life. Some bacterial lineages attempt evolutionary adaptations to the oxygen crisis, developing primitive antioxidant systems that can neutralize small quantities of reactive oxygen species. These early defenses include simple catalyses that decompose hydrogen peroxide, rudimentary superoxide dismutases that neutralize superoxide radicals, and modified cellular membranes that resist lipid peroxidation. But the adaptations emerge too slowly to save most anaerobic organisms from the rapidly rising oxygen concentrations. Scientists studying modern anaerobic bacteria find molecular evidence of this ancient poisoning. Many contemporary organisms that live in oxygen-free environments carry genes for primitive antioxidant enzymes, suggesting that their ancestors encountered oxygen stress during the Great Oxygenation Event. These molecular fossils reveal the evolutionary scars of the most successful mass poisoning in planetary history, genetic remnants of bacterial lineages that barely survived the transition to an oxygenated world. Only took oxygen concentrations of a few parts per million to begin killing organisms that had never encountered this molecular toxin. Only took trace amounts of atmospheric oxygen to overwhelm bacterial populations that had evolved no defenses against oxidative stress. Only took evolution's most successful innovation to create conditions that would eliminate most of the life that had flourished on Earth for 2 billion years. The mystery of survival puzzles. Biochemists who study the transition from anaerobic to aerobic life. How did any bacterial lineages survive oxygen concentrations that should have been universally lethal to reducing adapted organisms? Perhaps some populations lived in microenvironments where organic matter or metal sulfides provided local reducing conditions. Perhaps horizontal gene transfer allowed rapid sharing of primitive antioxidant systems between bacterial species. Ocean circulation patterns begin changing as the density differences between oxygenated and iron-rich waters create new current systems. Surface waters enriched with oxygen and depleted of dissolved iron develop different thermal properties than the metal-rich deep waters that maintain reducing conditions. These density gradients drive convection patterns that mix oxygenated surface waters deeper into ocean basins, expanding the kill zones where anaerobic bacteria cannot survive. The atmospheric chemistry becomes increasingly chaotic as oxygen reacts with methane, hydrogen sulfide, and ammonia in reactions that generate water vapor, carbon dioxide, and nitrogen compounds. The ancient greenhouse gases that maintained Earth's temperature balance for 2 billion years begin disappearing through oxidation reactions, setting the stage for climate changes that will compound the biological crisis with planetary cooling. Volcanic gases entering the atmosphere encounter oxygen for the first time, creating oxidation reactions that transform the composition of volcanic emissions. Sulfur dioxide oxidizes more rapidly in oxygenated atmospheres, creating sulfuric acid aerosols that reflect sunlight and contribute to atmospheric cooling. Hydrogen sulfide, a major component of ancient volcanic emissions, reacts with atmospheric oxygen to form sulfur compounds that alter cloud formation and precipitation patterns. The first breath becomes universal poison as oxygen concentrations rise beyond the tolerance limits of ancient life, killing organisms with the patient chemistry of molecular oxidation, eliminating bacterial populations that had dominated Earth's ecosystems since life began, creating the first mass extinction in planetary history through the simple act of breathing. Banded iron formations begin accumulating on ancient seafloors like geological calendars, recording the rhythm of atmospheric transformation in alternating layers of red and black minerals that will puzzle geologists for centuries. These distinctive rock formations emerge as the most visible evidence of the Great Oxygenation Event, created by the chemical dance between oxygen-producing cyanobacteria and the iron-rich oceans that have defined Earth's chemistry for 2 billion years. Each band represents a cycle of oxygen production and iron precipitation, a seasonal rhythm of life and death played out in mineral deposits. The formation process proceeds with chemical precision that modern laboratories struggle to replicate. During periods of high oxygen production, dissolved ferrous iron in ancient seawater oxidizes rapidly, forming ferric iron compounds that precipitate as red jasper, hematite, and other iron oxide minerals. When oxygen production decreases, perhaps during winter months or periods of reduced cyanobacterial activity, the iron precipitation slows, allowing organic matter and reduced minerals to accumulate in darker layers rich in magnetite and iron silicates. These alternating bands create some of Earth's most distinctive geological features, formations that can extend for hundreds of kilometers and reach thicknesses of several hundred meters. The Lake Superior region contains banded iron formations deposited over hundreds of millions of years, creating mineral wealth that will fuel human industrial development billions of years in the future. The Pilbara region of Western Australia preserves even older banded iron formations, some dating back 3.5 billion years to the earliest experiments in oxygenic photosynthesis. Geochemists studying these ancient formations find evidence of oxygen concentrations that fluctuated wildly during the early phases of atmospheric oxygenation. The iron oxide bands suggest periods when atmospheric oxygen reached levels of several percent, followed by intervals when oxygen disappeared almost entirely from the atmosphere. These oscillations indicate that the transition from anaerobic to aerobic Earth proceeded through multiple cycles of oxygenation and deoxygenation, perhaps driven by biological feedback mechanisms that modern scientists struggle to understand. The banding patterns reveal mysteries that challenge current understanding of ancient ocean chemistry. Some formations show daily layering, suggesting that tidal cycles influenced iron precipitation on ancient sea floors. Others display evidence of seasonal variations in oxygen production, indicating that even primitive cyanobacteria followed annual cycles of photosynthetic activity. Still others show disruptions in banding patterns that may record volcanic eruptions, meteorite impacts, or other catastrophic events that interrupted the steady rhythm of iron deposition. Scientists analyzing the mineral composition of banded iron formations discover trace elements that provide clues about ancient atmospheric conditions. Chromium isotope ratios suggest oxygen concentrations rose above 1% of modern levels during peak oxygenation events. Sulfur isotope signatures indicate that atmospheric chemistry oscillated between oxidizing and reducing conditions multiple times during the Great Oxygenation Event. These chemical fingerprints preserve information about atmospheric composition that no other geological formation can provide. Only took tens of millions of years to deposit iron formations containing more metal than all of humanity has ever mined. Only took the patient chemistry of oxygen and iron to create mineral deposits that represent the largest iron ore reserves on Earth. Only took cyanobacterial photosynthesis, this brief geological interval, to transform dissolved iron into solid minerals that will define planetary geology for billions of years. The deposition patterns suggest that ancient oceans stratified into distinct chemical layers during the Great Oxygenation Event. Surface waters, enriched with oxygen from cyanobacterial photosynthesis, developed oxidizing chemistry that precipitated iron rapidly. Deeper waters remained reducing, maintaining high concentrations of dissolved iron that could migrate upward into the oxygenated zones where precipitation occurred. This chemical stratification created ideal conditions for banded iron formation, with regular mixing events bringing iron-rich deep water into contact with oxygen-rich surface water. Modern analogues for banded iron formation chemistry exist in only a few locations on Earth. Lake Matano in Indonesia maintains stratified waters with oxygen-rich surface layers overlying iron-rich deep waters, creating conditions similar to ancient oceans. Studying these modern systems helps scientists understand the physical processes that created banded iron formations. But the scale of ancient iron deposition far exceeds anything observed in contemporary environments. The formations terminate abruptly in most locations around 2 billion years ago, marking the end of the chemical conditions that made their deposition possible. As atmospheric oxygen concentrations stabilized at higher levels, dissolved iron concentrations in seawater dropped permanently below the thresholds required for massive iron precipitation. The ancient iron-rich oceans that had characterized Earth for billions of years transformed into the iron-poor seas that dominate modern marine chemistry. Paleontologists studying banded iron formations find microfossils of the cyanobacteria responsible for their deposition. These ancient bacterial remains preserve cellular structures, organic molecules, and isotopic signatures that provide direct evidence of early photosynthetic life. Some formations contain fossilized stromatolites, layered bacterial mats that show the three-dimensional structure of ancient cyanobacterial communities. The economic significance of banded iron formations extends far beyond their scientific value. These deposits contain most of the world's iron ore reserves, including the massive formations that supply steel production for modern industrial civilization. The ancient bacterial crisis that nearly sterilized Earth also created the mineral wealth that enables technological societies, transforming biological waste into economic resources through geological processes that operated over hundreds of millions of years. Banded iron formations record the rhythm of atmospheric transformation in alternating layers of red and black minerals, preserving the chemical signatures of life's most successful innovation in geological calendars that chronicle the death of ancient worlds and the birth of oxygenated Earth. Ancient life retreats to oxygen-free refuges as the atmospheric transformation accelerates beyond the tolerance limits of organisms that have dominated Earth for 2 billion years. The survivors flee to deep ocean sediments where oxygen cannot penetrate, to hydrothermal vents where reducing chemistry still prevails, to anaerobic microenvironments that will become the last sanctuaries for reducing adapted life. These refuges represent evolutionary lifeboats, preserving bacterial lineages that would otherwise vanish completely from a planet increasingly hostile to their ancient chemistry. The deep subsurface becomes the most important refuge for anaerobic life during the Great Oxygenation Event. Sediments below the oxygen penetration depth maintain reducing conditions even as surface waters become increasingly oxygenated. Sulfate-reducing bacteria, methanogenic archaea, and fermentative organisms establish populations in these buried environments, creating underground ecosystems that persist largely unchanged for billions of years. Modern drilling projects discover these ancient bacterial communities living in rocks and sediments kilometers below Earth's surface, direct descendants of organisms that fled the oxygen crisis. Hydrothermal vents provide another crucial sanctuary for anaerobic life. The hot, metal-rich waters emerging from underwater volcanic systems maintain reducing chemistry through continuous influx of hydrogen sulfide, reduced metals, and organic compounds synthesized through Fischer-Tropsch reactions. Bacteria living near hydrothermal vents never experience oxygen stress because the vent chemistry neutralizes any dissolved oxygen that diffuses into their environment. These vent communities preserve metabolic pathways and cellular architectures that disappeared from most other marine environments during atmospheric oxygenation. Scientists studying modern hydrothermal vent ecosystems find bacterial communities that appear virtually identical to microfossils preserved in rocks deposited during the Great Oxygenation Event. The vent bacteria use metabolic pathways based on sulfur reduction, iron oxidation, and chemosynthetic carbon fixation that dominated ancient marine ecosystems. These organisms represent living fossils, biochemical time capsules that preserve the metabolic diversity of pre-oxygenation Earth in isolated reducing environments. Some bacterial lineages develop symbiotic relationships with other organisms as a survival strategy during the oxygen crisis. Anaerobic bacteria begin living inside the cells of larger microorganisms, creating endosymbiotic partnerships that protect both partners from oxygen toxicity. These early endosymbiotic relationships may have provided the evolutionary foundation for more complex cellular architectures, including the mitochondrial symbioses that will eventually enable oxygen-breathing life. The gut environments of early eukaryotic organisms become important refuges for anaerobic bacteria during the atmospheric transition. Even in an increasingly oxygenated world, digestive systems maintain reducing conditions where oxygen-sensitive bacteria can survive and reproduce. Modern animals still harbor diverse anaerobic bacterial communities in their digestive tracts. Descendants of organisms that survived the Great Oxygenation Event by taking shelter inside other life forms only took the oxygen crisis a few million years to drive most anaerobic life into marginal environments where they had never lived before. Only took atmospheric transformation this brief interval to convert surface-dwelling organisms into subsurface refugees, vent dwellers, and intestinal symbionts. Only took evolution's most successful innovation to force ancient life into hiding places where some populations remain to this day. The mystery of survival strategies puzzles microbiologists who study the transition from anaerobic to aerobic dominance. How did bacterial lineages with no previous experience of oxygen stress develop the physiological adaptations necessary to survive in refuge environments? Perhaps horizontal gene transfer accelerated the spread of stress resistance mechanisms between bacterial populations. Perhaps some organisms possessed dormancy capabilities that allowed them to survive periods of oxygen exposure. Seasonal refugees emerge as oxygen concentrations fluctuate with cyanobacterial productivity cycles. During winter months or periods of reduced photosynthetic activity, oxygen levels in surface waters drop enough to allow anaerobic organisms to recolonize habitats from which they had been excluded. These temporary refugees enable some bacterial populations to persist through the oxygen crisis by following seasonal migration patterns between oxygenated and reducing environments. Salt marshes and tidal pools develop into important refuges where anaerobic bacteria can survive in sediments that become oxygen-free during burial by tidal action. The rhythmic exposure and burial of tidal zone sediments create microenvironments where reducing chemistry persists even as atmospheric oxygen concentrations rise. Modern salt marsh sediments still harbor diverse anaerobic bacterial communities that may trace their ancestry to Great Oxygenation Event survivors. Volcanic hot springs provide refuge environments where high temperatures and reducing chemistry exclude oxygen from local ecosystems. Thermophilic bacteria living in these extreme environments never encounter oxygen concentrations high enough to cause cellular damage. Some modern hot spring bacterial communities preserve metabolic pathways that date back to the pre-oxygenation world, including sulfur-based metabolisms and carbon fixation mechanisms that disappeared from most other environments. The refuge environments develop their own ecological complexity as displaced anaerobic organisms establish new community structures in previously uninhabited niches. Competition for limited space in oxygen-free environments drives evolutionary innovations in bacterial metabolism, cellular architecture, and stress resistance. These innovations will eventually contribute to the metabolic diversity that characterizes modern anaerobic ecosystems. Deep ocean basins become stratified refuges where oxygen-depleted bottom waters maintain reducing conditions suitable for anaerobic life. The density differences between oxygenated surface waters and iron-rich deep waters create stable chemical gradients that persist for millions of years. Bacteria living in these deep refuge zones develop adaptations to low nutrient conditions, creating ecosystems based on extremely efficient resource cycling. Ancient life retreats to oxygen-free refuges with the desperation of organisms facing extinction, finding sanctuary in environments where reducing chemistry still prevails, establishing populations that will preserve the metabolic heritage of pre-oxygenation Earth in hidden corners of an increasingly hostile world. The methane greenhouse collapses as oxygen destroys the atmospheric chemistry that has maintained Earth's temperature balance for 2 billion years. What began as a biological innovation in ancient seas triggers a cascade of atmospheric reactions that will plunge the planet into its first global ice age. Methane molecules, which have trapped solar radiation with extraordinary efficiency in the ancient atmosphere, react with oxygen to form water vapor and carbon dioxide greenhouse gases far weaker than the methane they replace. The destruction proceeds through chain reactions that operate on molecular timescales but produce planetary consequences over millions of years. When oxygen encounters methane in the ancient atmosphere, it initiates combustion reactions that consume both gases simultaneously. Each methane molecule can trap 25 times more heat than carbon dioxide over century-long timescales, so its elimination from atmospheric chemistry represents a catastrophic reduction in greenhouse warming capacity. The ancient Earth loses its thermal blanket just as oxygen production reaches levels that sustain continuous atmospheric reactions. Atmospheric chemists studying the transition from methane-rich to oxygen-rich atmospheres calculate that methane concentrations must have dropped by orders of magnitude during the Great Oxygenation Event. Computer models suggest that atmospheric methane levels fell from perhaps 10,000 parts per million to less than 10 parts per million within a few million years, a geological instant that eliminated most of the greenhouse warming that had compensated for a weaker young sun. The methane sources begin failing as oxygen penetrates the reducing environments where methanogenic bacteria produce most atmospheric methane. Anaerobic organisms living in ocean sediments, tidal marshes, and hydrothermal systems generate methane through fermentation reactions that require strict oxygen-free conditions. As atmospheric oxygenation proceeds, these methane-producing environments shrink dramatically, reducing biological methane production to trace levels that cannot maintain atmospheric concentrations. Volcanic methane production also decreases, as atmospheric oxygen alters the chemistry of volcanic emissions. In reducing atmospheres, volcanic gases contain significant quantities of methane produced through Fischer-Tropsch synthesis reactions between carbon monoxide and hydrogen at high temperatures. But as atmospheric oxygen concentrations rise, these volcanic emissions encounter oxidizing conditions that convert methane to carbon dioxide and water vapor before the gas can accumulate in significant atmospheric concentrations. Scientists studying ancient volcanic rocks find evidence of this transition in the chemical composition of gas inclusions trapped in minerals during eruption events. Volcanic glasses deposited before the Great Oxygenation Event contain methane concentrations far higher than those found in post-oxygenation formations. These chemical fingerprints preserve direct evidence of the atmospheric transformation that eliminated Earth's methane greenhouse. Only took atmospheric oxygen concentrations of a few percent to begin destroying methane with chemical reactions that modern industrial processes struggle to replicate efficiently. Only took biological innovation this brief interval to eliminate greenhouse gases that had maintained planetary temperatures for longer than complex life has existed. Only took evolution's most successful waste product to trigger climate changes that would nearly freeze the planet that created it. The feedback mechanisms that might have stabilized atmospheric methane concentrations prove inadequate against the rising tide of oxygen production. Methanogenic bacteria cannot increase their metabolic output fast enough to compensate for accelerating methane destruction. Volcanic systems cannot generate enough reducing gases to maintain atmospheric methane levels against continuous oxidation. The ancient greenhouse system lacks the regulatory mechanisms necessary to survive the transition to an oxygenated world. Continental weathering patterns begin changing as the loss of atmospheric methane exposes surface rocks to temperature fluctuations that had been moderated by greenhouse warming for billions of years. The chemical weathering reactions that consume atmospheric carbon dioxide accelerate in response to temperature stress, creating additional cooling feedback that compounds the methane greenhouse collapse. Silicate weathering removes carbon dioxide from the atmosphere at rates that overwhelm volcanic carbon dioxide production. Ice albedo feedback amplifies the cooling as the first glacial ice begins forming at high latitudes. Ice reflects solar radiation more efficiently than the dark ocean waters it replaces, reducing the amount of solar energy absorbed by Earth's surface. As ice coverage expands, the planet's albedo increases, accelerating cooling in a positive feedback loop that will eventually drive global glaciation. The atmospheric chemistry becomes increasingly unstable as the methane greenhouse collapses through irreversible oxidation reactions. Mathematical models of ancient atmospheric evolution suggest that the transition from greenhouse to icehouse conditions proceeded through multiple tipping points, where small changes in oxygen production triggered large changes in atmospheric composition. These nonlinear transitions help explain why the Great Oxygenation Event produced such dramatic climate consequences from relatively modest changes in biological productivity. Ocean circulation patterns respond to the changing atmospheric chemistry, as the density differences between warming and cooling waters drive new current systems. The loss of atmospheric methane creates stronger temperature gradients between equatorial and polar regions, intensifying atmospheric circulation and ocean mixing. These circulation changes distribute the cooling effects of methane loss more rapidly around the planet, accelerating the transition to icehouse conditions. Paleoclimatologists studying the transition from greenhouse to icehouse Earth find evidence of rapid climate change in sedimentary rocks deposited during the methane collapse. Dropstones rocks carried by icebergs and deposited in marine sediments begin appearing in tropical latitudes for the first time in Earth's history. Glacial till deposits indicate ice sheet formation at sea level near the equator, suggesting that the methane greenhouse collapse produced cooling more severe than any subsequent ice age. The methane greenhouse collapses through atmospheric chemistry that transforms Earth's climate system from greenhouse stability to icehouse instability, eliminating the thermal regulation that has maintained liquid oceans for 2 billion years, setting the stage for the most severe glaciation in planetary history. Snowball Earth encases the planet in glacial silence as ice sheets advance from both poles, meeting at the equator to entomb continents in frozen crystalline armor that reflects sunlight back to space with mathematical precision. The global glaciation represents the most extreme climate state in Earth's history, a planetary deep freeze that transforms the blue-green world of ancient seas into a white sphere of ice and snow that persists for millions of years. Ocean surfaces freeze to depths of hundreds of meters, creating barriers between marine life and the atmosphere that will fundamentally alter the chemistry of both. The glaciation begins at high latitudes, where the loss of atmospheric methane creates temperature conditions that can no longer prevent ice formation during winter months. Initial ice coverage expands slowly, advancing and retreating with seasonal temperature cycles, but the ice albedo feedback ensures that each winter's ice formation reflects more sunlight than the previous year. Summer melting becomes progressively less effective at removing winter ice accumulation, creating permanent ice sheets that begin flowing toward lower latitudes under their own gravitational weight. Continental ice sheets reach thicknesses of several kilometers as they advance toward equatorial regions, carrying enough gravitational potential energy to reshape the planetary surface through erosional processes that operate on geological timescales. The ice flows carve valleys, transport boulders across thousands of kilometers, and deposit glacial sediments that will preserve evidence of this global freeze for billions of years. Geologists studying ancient glacial deposits find dropstones, rocks carried by icebergs in sedimentary formations deposited near sea level in tropical paleolatitudes. Ocean ice formation proceeds through different mechanisms than continental glaciation, creating sea ice that grows from the surface downward as atmospheric temperatures drop below the freezing point of seawater. The salinity of ancient oceans affects ice formation rates, with high concentrations of dissolved minerals lowering the freezing point and creating unstable ice that forms and melts repeatedly before establishing permanent coverage. But as global temperatures continue dropping, even the mineral-rich ancient seas freeze solid to depths that isolate marine ecosystems from atmospheric contact. The planetary energy balance shifts dramatically as ice coverage increases Earth's albedo from approximately 0.3 to nearly 0.7, reflecting most incoming solar radiation back to space rather than absorbing it as heat. This albedo change creates a runaway cooling effect that drives global temperatures well below the freezing point of seawater. Computer models of snowball Earth conditions suggest that global average temperatures drop to perhaps minus 40 degrees Celsius, creating surface conditions more severe than modern Antarctica. Scientists studying the snowball Earth hypothesis find geological evidence of global glaciation in rock formations on every continent, including glacial sediments deposited at sea level in paleotropical regions where ice formation should be impossible under normal climate conditions. The distribution of these glacial deposits suggests that ice coverage extended from pole to pole, creating the most comprehensive glaciation in planetary history. Carbon isotope ratios in sediments deposited during the glaciation indicate that biological productivity nearly ceased during the frozen intervals. Only took the loss of atmospheric methane a few million years to trigger ice albedo feedback strong enough to freeze the entire planetary surface. Only took the collapse of the ancient greenhouse system this brief interval to create climate conditions more extreme than Mars experiences today. Only took evolution's oxygen innovation to lock Earth in a deep freeze that persisted for tens of millions of years. The mystery of survival during snowball Earth conditions puzzles astrobiologists who study the limits of life in extreme environments. How did any organisms survive global ice coverage that isolated marine ecosystems from atmospheric contact for millions of years? Perhaps volcanic activity created ice-free refuges around hydrothermal vents and hot springs. Perhaps the ice coverage was incomplete, leaving patches of open ocean where life could persist in reduced populations. Volcanic islands provide the most plausible refuges for surface life during snowball Earth glaciation. Active volcanoes generate enough heat to maintain ice-free zones where liquid water can exist even during global freeze conditions. These volcanic oases become isolated ecosystems where surviving organisms evolve in response to extreme environmental stress. Modern studies of life in polar regions and high-altitude environments provide analogues for the survival strategies that might have enabled persistence during global glaciation. The ice itself becomes a habitat for specialized organisms that develop adaptations to sub-freezing temperatures and limited nutrient availability. Modern studies of life in Arctic sea ice reveal diverse microbial communities that survive by extracting energy from chemical gradients within the ice matrix. Similar communities may have evolved during snowball Earth glaciation, creating ice-based ecosystems that persisted throughout the frozen intervals. Atmospheric chemistry simplifies dramatically during snowball Earth conditions as most biological processes cease, and volcanic outgassing becomes the dominant source of atmospheric gases. Carbon dioxide accumulates gradually as volcanic emissions continue, but biological carbon fixation nearly stops. This carbon dioxide accumulation eventually provides the greenhouse warming necessary to melt the global ice coverage. But the process requires millions of years of volcanic activity to overcome the albedo feedback that maintains the frozen state. Geochemical cycles slow to geological timescales during snowball Earth, as the frozen surface prevents most water rock interactions that drive chemical weathering and mineral cycling. The ice-covered continents become chemically isolated from atmospheric contact, preserving ancient weathering surfaces that will be exposed when the ice finally melts. These preserved surfaces provide geological snapshots of pre-glaciation conditions, including evidence of the atmospheric chemistry that existed before the methane greenhouse collapsed. Ocean chemistry beneath the ice undergoes dramatic changes as biological productivity drops to near zero levels, and chemical processes operate in isolation from atmospheric contact. The ice cover prevents gas exchange between seawater and atmosphere, allowing dissolved gases to accumulate to concentrations that would be impossible in ice-free oceans. Some geochemical models suggest that ocean chemistry became increasingly reducing beneath the ice as oxygen consumption continued while oxygen production nearly ceased. Snowball Earth encases the planet in glacial silence that transforms the ancient world into a frozen sphere where life retreats to marginal refuges, where ice albedo feedback maintains surface temperatures below the limits of most biological processes, where volcanic carbon dioxide accumulates slowly in the atmosphere while evolution waits for the greenhouse warming that will eventually melt the global freeze. Life endures beneath the ice in pockets of liquid water and volcanic hot springs where the chemistry of survival operates by rules that have never applied to surface ecosystems. These refuges become evolutionary laboratories where organisms develop adaptations to extreme cold, limited nutrients, and isolation from atmospheric contact that will persist for millions of years. The survivors represent biological time capsules, preserving genetic lineages through conditions more severe than any subsequent crisis in Earth's history. evolving innovations that will contribute to life's eventual recovery when the ice finally melts. Beneath kilometers of glacial ice, liquid water persists in geothermal environments where volcanic heat maintains temperatures above freezing despite surface conditions that approach absolute zero in some regions. These subglacial lakes and hydrothermal pools become isolated ecosystems where evolution proceeds in complete darkness, driven by chemical energy rather than photosynthesis. Modern studies of subglacial lakes in Antarctica reveal diverse microbial communities that have survived in isolation for millions of years, providing analogues for life during snowball Earth conditions. The organisms that survive develop metabolic innovations that extract energy from chemical gradients unavailable to surface-dwelling life. Some bacteria learn to respire sulfate in environments where dissolved oxygen concentrations drop to zero, creating metabolic pathways that will persist long after atmospheric oxygenation resumes. Others develop enhanced capabilities for nitrogen fixation, converting atmospheric nitrogen into biological compounds in environments where fixed nitrogen becomes limiting for biological productivity. Volcanic hot springs provide the most stable refuges for complex microbial communities during global glaciation. The continuous heat flow from underground magma chambers maintains liquid water and drives chemical reactions that produce hydrogen sulfide, methane, and other reduced compounds that serve as energy sources for chemosynthetic bacteria. These hot spring ecosystems develop their own food webs based entirely on chemical energy, creating biological complexity that persists independently of photosynthetic primary production. Scientists studying modern extremophile organisms find metabolic capabilities that may have evolved during snowball Earth conditions. Some bacteria can survive temperatures approaching the freezing point of cellular fluids, while others tolerate salinity levels that approach the saturation limits of dissolved minerals. These extreme adaptations suggest evolutionary responses to environmental conditions that no longer exist on Earth's surface, but may have characterized refuge environments during global glaciation. The genetic innovations that emerge during snowball Earth survival include enhanced DNA repair mechanisms that protect genetic information from damage caused by freezing and thawing cycles. Some organisms develop antifreeze proteins that prevent ice crystal formation within cellular structures, while others produce cryoprotectant compounds that stabilize cellular membranes at sub-freezing temperatures. These molecular adaptations represent evolutionary solutions to environmental problems that most life had never encountered. Only took global glaciation a few million years to drive evolution into environmental extremes where most biological processes had never operated before. Only took snowball Earth conditions this brief interval to force life into refuges where chemical energy replaced solar energy as the foundation of ecosystem productivity. Only took the most severe climate crisis in planetary history to generate biological innovations that would expand the environmental range where life could survive. The mystery of genetic diversity preservation puzzles evolutionary biologists who study survival through extreme bottleneck events. How did microbial populations maintain enough genetic variation to fuel evolutionary recovery when the ice finally melted? Perhaps horizontal gene transfer accelerated genetic exchange between isolated populations. Perhaps some organisms developed enhanced mutation rates that generated genetic diversity more rapidly than normal evolutionary processes. Ice-based ecosystems develop within the glacial ice itself as specialized organisms adapt to life within the crystal matrix that forms the frozen ocean surface. These ice-dwelling communities extract nutrients from atmospheric dust trapped within the ice, from chemical reactions between ice and dissolved minerals, and from metabolic products of other ice-adapted organisms. Modern studies of sea ice microbiology reveal complex food webs that exist entirely within frozen seawater, suggesting analogous communities during snowball Earth glaciation. Deep ocean basins become isolated chemical reactors where biological and geological processes operate in complete isolation from surface conditions. The thick ice cover prevents atmospheric gas exchange, allowing dissolved gases to accumulate to concentrations far higher than ice-free oceans could sustain. Some geochemical models suggest that deep ocean chemistry became increasingly reducing during snowball Earth, creating environmental conditions that favored anaerobic organisms displaced by earlier atmospheric oxygenation. Tidal heating maintains liquid water in some coastal environments where gravitational forces from the moon generate enough mechanical energy to prevent complete freezing. These tidal refuges create periodic access to liquid water for organisms that can survive freeze-thaw cycles, enabling some surface-adapted organisms to persist through global glaciation. The tidal refuges also provide mixing zones where nutrients concentrated during freezing events become available for biological uptake during brief melting intervals. Subsurface ecosystems expand dramatically during snowball Earth as organisms retreat to greater depths where geothermal heating maintains liquid water and reducing chemistry. The deep subsurface becomes a vast refuge where bacterial communities develop enhanced capabilities for survival in low-energy environments. These subsurface populations preserve metabolic diversity that will eventually recolonize surface environments when glacial conditions end. Volcanic eruptions through glacial ice create temporary refuges where volcanic heat and chemical emissions generate localized ecosystems that persist for thousands of years before freezing over again. These ephemeral volcanic oases become stepping stones that enable some organisms to survive through multiple glacial cycles. Maintaining genetic connections between isolated refugee populations that might otherwise diverge beyond the possibility of genetic exchange. Life endures beneath the ice through biological innovations that extract energy from chemical sources, that tolerate extreme cold and chemical isolation, that preserve genetic diversity through the most severe environmental crisis in planetary history, waiting in thermal refuges for the volcanic carbon dioxide that will eventually melt the global freeze and enable life's return to surface environments. The great dying of ancient worlds proceeds with the inexorable chemistry of planetary transformation as anaerobic ecosystems that flourished for billions of years vanish forever, leaving only chemical traces in rocks that will puzzle geologists for the rest of Earth's history. This represents the first mass extinction in planetary time. But unlike later catastrophes driven by asteroids or volcanism, this dying emerges from life's own success, from the biological innovation that produces oxygen as waste and transforms that waste into the most effective poison in evolutionary history. Entire bacterial lineages disappear from the fossil record during the transition to an oxygenated world, eliminated not through competition or predation, but through the fundamental incompatibility between their cellular chemistry and the new atmospheric conditions. These extinct organisms represent billions of years of evolutionary innovation, metabolic pathways more diverse than anything that will evolve afterward, cellular architectures adapted to environmental conditions that will never exist again on Earth's surface. The extinction proceeds through multiple mechanisms that operate simultaneously across all marine environments. Direct oxygen toxicity kills organisms whose cellular machinery cannot tolerate oxidizing conditions, while indirect effects eliminate organisms whose food sources disappear as ecosystem chemistry changes. Anaerobic bacteria that depend on reduced sulfur compounds, ferrous iron, and organic matter find their energy sources oxidized beyond biological utility by the rising oxygen concentrations. Sulfate-reducing bacteria lose access to the hydrogen sulfide that has powered their metabolism for 2 billion years, as atmospheric oxygen converts sulfur compounds to sulfates that require different metabolic pathways. Methanogenic archaea find their methane production neutralized by atmospheric oxidation reactions that consume methane faster than biological processes can produce it. Iron-reducing bacteria discover that dissolved iron disappears from oxygenated seawater, precipitating as iron oxides that settle beyond the reach of their metabolic systems. The chemical signatures of this ancient dyeing persist in sedimentary rocks as distinctive carbon isotope ratios that record the collapse of anaerobic carbon cycling. Geochemists studying rocks deposited during the Great Oxygenation Event find evidence of massive organic matter burial, suggesting that dead anaerobic organisms accumulated faster than decomposition processes could recycle their carbon. The isotope signatures indicate that biological productivity crashed in many environments as anaerobic primary producers died without immediate replacement by oxygen-tolerant organisms. Scientists studying modern anaerobic environments find evolutionary relics of this ancient catastrophe in the genetic sequences of surviving organisms. Many contemporary bacteria carry pseudogenes, non-functional genetic remnants of proteins that once enabled survival in pre-oxygenation environments. These molecular fossils provide evidence of metabolic capabilities that were lost during the transition to an oxygenated world, suggesting that the genetic diversity eliminated during the Great Dying far exceeded the diversity that survived. Only took rising oxygen concentrations a few million years to eliminate bacterial lineages that had dominated Earth's ecosystems for longer than complex life has existed. Only took atmospheric transformation this brief geological interval to destroy metabolic innovations that evolution had required billions of years to develop. Only took life's most successful waste product to create the first mass extinction in planetary history through the simple chemistry of oxidation. The dying creates ecological vacuums that persist for millions of years before oxygen-tolerant organisms evolve to fill the empty niches. Primary productivity crashes in many marine environments as photosynthetic bacteria adapted to reducing conditions die without immediate replacement by cyanobacteria, which remain limited to specific environmental niches during the early phases of atmospheric oxygenation. The collapse of primary productivity triggers cascading extinctions through food webs that had depended on anaerobic organisms for billions of years. Some bacterial lineages attempt evolutionary rescue through rapid adaptation to oxidizing conditions, developing primitive antioxidant systems and modified metabolic pathways that can tolerate low oxygen concentrations. But the pace of atmospheric change overwhelms most adaptive responses. Eliminating organisms faster than evolution can generate survival mechanisms. The few lineages that successfully adapt become the ancestors of all subsequent life, but they represent a tiny fraction of the metabolic diversity that existed before atmospheric oxygenation. Deep-sea environments become mass graveyards where the chemical signatures of ancient life accumulate in sediment layers that record the scale of biological catastrophe. Organic matter from dead anaerobic organisms creates reducing microenvironments within otherwise oxygenated sediments, preserving chemical fossils of extinct metabolisms. These buried organic deposits will eventually become petroleum and natural gas, transforming biological catastrophe into energy resources that will power technological civilizations billions of years in the future. The extinction patterns vary between different marine environments as local chemical conditions determine which organisms survive and which disappear. Shallow seas with high cyanobacterial productivity experience the most severe extinctions, while deeper waters and sediment environments retain some anaerobic organisms in refuges where oxygen penetration remains limited. These spatial patterns of survival and extinction create the biogeographical foundations for all subsequent evolution. Volcanic systems provide temporary refuges where reducing chemistry persists long enough for some anaerobic organisms to survive the initial phases of atmospheric oxygenation. Hydrothermal vents, volcanic hot springs, and regions of active volcanism maintain local reducing conditions that neutralize dissolved oxygen, creating islands of ancient chemistry in an increasingly oxidized world. But even these refugees experience chemical changes as atmospheric oxygenation alters the composition of volcanic gases and hydrothermal emissions. The Great Dying eliminates not just individual species, but entire categories of metabolism that will never evolve again. Some bacterial lineages possess metabolic capabilities so specialized for reducing environments that no evolutionary pathway exists for adapting them to oxidizing conditions. These lost metabolisms represent irreversible evolutionary dead ends, biological innovations that required billions of years to develop but could not survive the chemical transformation of planetary environments. Paleontologists studying the Great Oxygenation Event find evidence that recovery from this ancient mass extinction required tens of millions of years, far longer than recovery from later extinction events caused by asteroids or volcanism. The fundamental nature of the environmental change, from reducing to oxidizing planetary chemistry, necessitated evolutionary innovations at the cellular level that proceed much more slowly than ecological recovery from physical catastrophes. The Great Dying of ancient worlds proceeds through chemical transformation that eliminates billions of years of evolutionary innovation, destroying anaerobic ecosystems that had defined life on Earth since its beginning, leaving only chemical traces of metabolic diversity that will never be recovered in the oxygenated world that emerges from this biological catastrophe. Oxygen levels fluctuate and stabilize through geological feedback mechanisms that operate on timescales spanning millions of years, creating the first regulatory systems capable of maintaining atmospheric composition within ranges compatible with complex life. The violent oscillations of the early oxygenation period gradually dampen into controlled cycles as Earth develops chemical and biological buffers that prevent the extreme atmospheric swings that characterize the initial transition from anaerobic to aerobic environments. This stabilization represents one of the most important developments in planetary evolution, establishing the atmospheric foundation for all subsequent biological complexity. The fluctuations proceed through boom and bust cycles that reflect the immature state of early oxygen regulation. Periods of high cyanobacterial productivity drive atmospheric oxygen to concentrations approaching modern levels, followed by crashes that eliminate most free oxygen from the atmosphere for millions of years. These oscillations appear in the geological record as alternating oxidized and reduced sediment layers, chemical signatures of an unstable atmospheric system searching for equilibrium between oxygen production and consumption. Atmospheric chemists studying the transition from unstable to stable oxygenation identify several feedback mechanisms that eventually bring oxygen cycling under control. The evolution of oxygen-breathing organisms creates biological sinks that consume atmospheric oxygen at rates proportional to its concentration, providing negative feedback that prevents unlimited oxygen accumulation. The development of aerobic decomposition processes ensures that organic matter burial, which removes oxygen-consuming material from circulation, becomes self-limiting as oxygen levels rise. The carbon cycle undergoes fundamental reorganization as oxygen-dependent processes begin controlling the rates of organic matter production, burial, and decomposition. In pre-oxygenation environments, organic carbon cycling operated primarily through anaerobic fermentation and sulfate reduction. But as atmospheric oxygen stabilizes, aerobic respiration becomes the dominant mechanism for organic matter decomposition, creating more efficient carbon cycling that maintains closer coupling between primary productivity and decomposition rates. Sulfur cycling develops new pathways as atmospheric oxygen enables the evolution of sulfur-oxidizing bacteria that can extract energy from reduced sulfur compounds produced by anaerobic organisms. This creates biogeochemical loops where sulfate reduction in oxygen-free environments produces hydrogen sulfide that sulfur-oxidizing bacteria consume in oxygenated zones, generating sulfate that completes the cycle. These coupled redox reactions provide stability to both oxygen and sulfur concentrations in marine environments. Scientists studying ancient atmospheric evolution find evidence of regulatory mechanisms that have no modern analogues. Some feedback systems appear to have operated through coupling between atmospheric oxygen and greenhouse gas concentrations, with oxygen levels controlling methane oxidation rates that influenced planetary temperature and climate stability. These ancient regulatory mechanisms may have provided more precise atmospheric control than contemporary systems, which lack the extreme chemical gradients that characterized early oxygenated environments. Only took planetary evolution tens of millions of years to develop atmospheric regulation systems capable of maintaining oxygen concentrations within narrow ranges. Only took biological innovation this brief interval to create feedback mechanisms that prevented the extreme atmospheric oscillations that had characterized early oxygenation. Only took life's collective metabolism, this geological moment, to establish atmospheric stability that has persisted for 2 billion years. The mystery of oxygen regulation puzzles atmospheric scientists who study the mechanisms that maintain modern oxygen concentrations near 21% of atmospheric composition. Computer models suggest that oxygen levels should fluctuate much more wildly than observations indicate, implying regulatory mechanisms that current science does not fully understand. Perhaps biological feedback operates through pathways more complex than simple consumption and production rates. Perhaps geological processes provide additional buffering capacity that models underestimate. Iron cycling develops new regulatory functions as atmospheric oxygenation creates oxidized iron minerals that can store and release electrons in response to changing redox conditions. The massive banded iron formations deposited during early oxygenation become geological batteries that absorb excess oxygen during periods of high production and release reducing equivalents during periods of oxygen depletion. These iron-based regulatory systems provide chemical buffering that moderates atmospheric oxygen fluctuations. Ocean circulation patterns evolve to support stable oxygen cycling, as the density differences between oxygenated and reduced waters drive currents that distribute oxygen more uniformly through marine environments. The development of thermohaline circulation creates global mixing patterns that prevent the formation of large oxygen-depleted zones that could destabilize atmospheric regulation. These circulation improvements reduce the spatial variability in oxygen concentrations that had characterized early oxygenated oceans. Biological evolution accelerates the development of regulatory mechanisms as organisms adapt to stable oxygen concentrations and begin depending on atmospheric regulation for their survival. The evolution of aerobic respiration creates organisms with metabolic rates that scale directly with atmospheric oxygen concentrations, providing automatic feedback that adjusts biological oxygen consumption in response to atmospheric changes. These biological regulators become more sophisticated over geological time as organisms develop increasingly complex oxygen-dependent metabolisms. Phosphorus cycling emerges as a crucial control mechanism for oxygen regulation as atmospheric oxygenation alters the chemistry of phosphorus weathering and deposition. Phosphorus availability limits primary productivity in many marine environments, so changes in phosphorus cycling directly control rates of oxygen production through photosynthesis. The evolution of phosphorus-concentrating mechanisms in marine organisms creates biological control over primary productivity that helps stabilize atmospheric oxygen. Volcanic outgassing rates adjust to changing atmospheric composition as the chemical interaction between volcanic gases and atmospheric oxygen creates new equilibrium conditions. Reduced volcanic gases react with atmospheric oxygen to produce oxidized emissions that have different effects on atmospheric chemistry. These volcanic adjustments provide geological feedback that helps maintain atmospheric stability over million-year timescales. The stabilization enables the evolution of organisms with complex oxygen requirements that could not survive in unstable atmospheric conditions. Early eukaryotic cells develop aerobic respiration systems that depend on steady oxygen availability, creating biological systems too complex to tolerate the wild atmospheric fluctuations that characterized early oxygenation. The atmospheric stability becomes a prerequisite for biological complexity that will eventually enable multicellular life. Oxygen levels fluctuate and stabilize through the evolution of regulatory mechanisms that couple biological, chemical, and geological processes into integrated systems capable of maintaining atmospheric composition within ranges compatible with complex life, establishing the foundation for billions of years of stable atmospheric evolution. New chemistry enables complex cells as oxygen availability unlocks metabolic pathways that generate energy with unprecedented efficiency, transforming single-celled organisms from simple bacteria into sophisticated eukaryotic cells capable of supporting the energy demands of complex biological structures. The transition from anaerobic to aerobic metabolism represents the most important biochemical revolution since the origin of life itself, providing the energetic foundation that will eventually enable multicellular organisms, tissue differentiation, and the biological complexity that characterizes modern ecosystems. Mitochondria emerge through endosymbiotic relationships between oxygen-breathing bacteria and larger host cells that cannot survive in oxygenated environments without symbiotic protection. These partnerships begin as defensive alliances where aerobic bacteria provide oxygen detoxification services for anaerobic hosts, but they evolve into intimate metabolic integration where bacterial symbionts become specialized organelles dedicated to energy production. The mitochondrial innovation multiplies cellular energy output by factors of 10 to 15 compared to anaerobic metabolism. The biochemistry of aerobic respiration operates through electron transport chains that extract energy from organic molecules with mathematical precision unavailable to anaerobic metabolisms. Where fermentation and anaerobic respiration can generate 2 to 4 molecules of ATP per glucose molecule, aerobic respiration produces 36 to 38 ATP molecules from the same starting material. This efficiency revolution enables cellular processes that require energy investments beyond the capacity of anaerobic organisms. Scientists studying modern mitochondria find genetic evidence of their bacterial ancestry in DNA sequences that more closely resemble bacterial genomes than eukaryotic nuclear DNA. Mitochondrial ribosomes, protein synthesis machinery, and metabolic pathways retain characteristics of free-living bacteria, suggesting that the endosymbiotic transition occurred through gradual integration rather than sudden cellular capture. Some mitochondrial genes have transferred to nuclear chromosomes over evolutionary time, creating genetic integration between host and symbiont that makes their separation impossible. The oxygen chemistry that enables aerobic respiration also creates new challenges for cellular survival, as reactive oxygen species generated during electron transport can damage DNA, proteins, and cellular membranes. Early eukaryotic cells develop sophisticated antioxidant systems that neutralize superoxide radicals, hydrogen peroxide, and hydroxyl radicals produced as byproducts of mitochondrial metabolism. These protective mechanisms represent evolutionary innovations that had no precedent in anaerobic cellular biology. Chloroplasts evolve through similar endosymbiotic processes as cyanobacteria become integrated into eukaryotic cells that can combine photosynthesis with aerobic respiration in the same organism. This dual metabolic capability creates the first organisms that can both produce and consume oxygen, providing metabolic flexibility that enables survival in environments where oxygen concentrations fluctuate rapidly. The combination of photosynthesis and respiration in single cells becomes the foundation for plant evolution. Only took the availability of atmospheric oxygen a few tens of millions of years to enable the evolution of cellular complexity that had been impossible during 2 billion years of anaerobic life. Only took aerobic metabolism this brief interval to provide the energy foundation for biological innovations that would transform planetary ecosystems. Only took mitochondrial symbiosis this geological moment to unlock the energetic potential that enables complex multicellular life. The mystery of eukaryotic origins puzzles evolutionary biologists who study the transition from prokaryotic to eukaryotic cellular organization. How did the complex cellular structures characteristic of eukaryotes, nuclei, endoplasmic reticulum, Golgi apparatus evolve so rapidly after billions of years of bacterial simplicity? Perhaps the energy abundance provided by mitochondrial respiration enabled cellular investments in structural complexity that anaerobic metabolism could never support. Cellular size increases dramatically as aerobic metabolism provides energy sufficient to maintain larger cell volumes and more complex internal organization. Anaerobic cells remain constrained by surface area to volume ratios that limit their maximum size, but aerobic cells can grow to sizes hundreds of times larger than their anaerobic ancestors. This size increase enables cellular specialization, internal compartmentalization, and the structural foundations necessary for multicellular organization. DNA repair mechanisms become more sophisticated as aerobic metabolism generates reactive oxygen species that damage genetic material at rates far higher than anaerobic environments. Eukaryotic cells develop multiple DNA repair pathways, proofreading mechanisms, and chromosomal protection systems that maintain genetic integrity despite the oxidative stress created by their own metabolism. These innovations enable the genetic stability necessary for complex multicellular development. Sexual reproduction evolves as a mechanism for managing the genetic damage caused by oxidative stress in aerobic organisms. The combination of genetic material from two parents provides opportunities for repairing damaged DNA sequences and eliminating harmful mutations that accumulate in lineages exposed to reactive oxygen species. Sexual reproduction becomes more advantageous in oxygenated environments where genetic damage rates exceed the repair capacity of individual organisms. Cellular communication systems develop new complexity as aerobic metabolism enables the energy-expensive processes of signal production, detection, and response that coordinate activities between different cells. Chemical signaling, electrical communication, and mechanical coordination require energy investments that anaerobic metabolism cannot sustain. The development of intercellular communication becomes prerequisite for multicellular organization, where cellular activities must be coordinated across entire organisms. Protein folding and enzyme function become more sophisticated as aerobic metabolism provides energy for maintaining complex protein structures that would be thermodynamically unstable in low-energy anaerobic systems. The availability of abundant ATP enables molecular chaperones, protein quality control systems, and enzyme regulation mechanisms that support the biochemical complexity necessary for advanced cellular functions. Cytoskeletal systems evolved to support larger cell sizes and more complex internal organization, as aerobic metabolism provides energy for maintaining structural proteins that organize cellular contents. Microtubules, microfilaments, and intermediate filaments create internal scaffolding that enables cellular movements, organelle positioning, and the structural integrity necessary for complex cell shapes. These cytoskeletal innovations become foundations for cellular specialization in multicellular organisms. Membrane systems become more elaborate as aerobic cells develop internal compartments that separate different metabolic processes and create specialized environments for specific biochemical functions. The endoplasmic reticulum, Golgi apparatus, and other membrane systems enable cellular complexity that would be impossible in simple bacterial cells. These internal membrane systems also provide additional surface area for metabolic processes without increasing overall cell size. New chemistry enables complex cells through aerobic metabolism that provides energy abundance sufficient to support cellular complexity. Endosymbiotic relationships that create sophisticated organelles, and biochemical innovations that manage the challenges of oxygen-based metabolism while unlocking its enormous energetic potential. The ozone shield forms above as high-altitude oxygen transforms into Earth's first sunscreen, creating a molecular barrier that filters deadly ultraviolet radiation and makes dry land habitable for the first time in planetary history. This atmospheric transformation proceeds through photochemical reactions that occur in the stratosphere, where solar radiation splits oxygen molecules into reactive atoms that recombine to form ozone, a 3-atom oxygen molecule that absorbs ultraviolet light with extraordinary efficiency. The ozone layer becomes one of life's most important innovations, an atmospheric protection system that enables the colonization of terrestrial environments. The formation process requires oxygen concentrations to reach approximately 10% of modern atmospheric levels before significant ozone production becomes possible. Below this threshold, oxygen molecules remain too sparse in the stratosphere to sustain the photochemical reactions that create ozone. Above this threshold, ozone formation accelerates rapidly, creating a protective layer that can absorb more than 90% of harmful ultraviolet radiation before it reaches Earth's surface. This represents a critical transition in planetary habitability, transforming land surfaces from sterilized wastelands into environments suitable for biological colonization. Ultraviolet radiation had sterilized terrestrial environments for billions of years before ozone formation, creating surface conditions where organic molecules decompose faster than biological processes can produce them. The intense ultraviolet flux from the young sun, combined with the absence of atmospheric shielding, made land surfaces uninhabitable for any form of life. Even simple organic compounds essential for biological chemistry could not persist on exposed surfaces, limiting life to underwater environments where liquid water provided natural ultraviolet protection. Scientists studying the transition from uninhabitable to habitable land surfaces find geological evidence of the ozone formation process in ancient soils and mineral deposits. Rocks exposed to pre-ozone surface conditions show distinctive weathering patterns created by ultraviolet photochemistry that ceased abruptly when atmospheric shielding developed. The transition appears in sedimentary sequences as a sharp change from sterile mineral deposits to formations containing the first traces of terrestrial organic matter. The ozone chemistry operates through catalytic cycles that amplify the protective effects of relatively small atmospheric oxygen concentrations. Individual ozone molecules absorb ultraviolet photons and dissociate into oxygen atoms that can recombine with other oxygen molecules to form new ozone. This recycling process enables a thin ozone layer to provide comprehensive ultraviolet protection for entire planetary surfaces. The catalytic efficiency of ozone formation represents one of the most elegant solutions to environmental problems that life has ever evolved. Atmospheric physicists studying ozone formation find that the process requires specific altitude ranges where temperature and pressure conditions favor ozone production over ozone destruction. The stratosphere provides ideal conditions because its temperature profile and chemical composition minimize ozone-destroying reactions while maximizing ozone-producing photochemistry. This precise atmospheric layering suggests that planetary atmospheres must evolve specific structural characteristics to develop effective ultraviolet shielding. Only took atmospheric oxygen accumulation a few million years to reach concentrations sufficient for ozone layer formation that could protect entire continental surfaces from ultraviolet sterilization. Only took photochemical processes this brief interval to create atmospheric shielding more effective than any technological system humans have developed. Only took life's oxygen waste product this geological moment to solve the ultraviolet radiation problem that had prevented terrestrial colonization for billions of years. The mystery of ozone layer stability puzzles atmospheric chemists who study the balance between ozone production and destruction in modern atmospheres. Ozone molecules remain inherently unstable, with individual molecules persisting for only days to weeks before decomposing back into oxygen. Yet the ozone layer maintains consistent protective coverage across geological timescales, suggesting regulatory mechanisms that stabilize ozone concentrations despite continuous molecular turnover. Volcanic emissions begin interacting with the ozone layer as atmospheric chemistry becomes more complex, creating feedback loops between geological and atmospheric processes. Some volcanic gases, particularly sulfur compounds, can temporarily deplete ozone concentrations, reducing ultraviolet protection during periods of intense volcanic activity. These interactions suggest that ozone layer formation required not just adequate oxygen concentrations, but also relatively stable volcanic outgassing that would not overwhelm the atmospheric chemistry necessary for ozone maintenance. Surface temperatures begin changing as ozone formation alters the thermal properties of the stratosphere. Ozone absorbs both ultraviolet radiation and infrared radiation, creating warming in the stratosphere while providing cooling at Earth's surface. These temperature changes affect atmospheric circulation patterns, weather systems, and climate stability in ways that influence the habitability of terrestrial environments beyond simple ultraviolet protection. The first organic compounds begin accumulating on land surfaces as ultraviolet protection enables the preservation of carbon-based molecules in terrestrial environments. These early organic deposits remain largely abiotic products of atmospheric chemistry rather than biological activity, but they create chemical foundations that will eventually support terrestrial life. The accumulation of surface organics represents the first step toward developing soil chemistry capable of supporting plant growth. Continental weathering patterns change dramatically as ozone protection enables new chemical processes on exposed rock surfaces. Without ultraviolet sterilization, surface minerals begin developing chemical weathering reactions that include organic components, creating the first protosoils on continental surfaces. These early weathering processes remain slow compared to modern soil formation, but they represent fundamental changes in surface chemistry that make terrestrial environments more hospitable to life. Atmospheric chemistry becomes more stable as ozone formation provides negative feedback that regulates oxygen concentrations through ultraviolet shielding effects. High ozone concentrations reduce surface ultraviolet flux, which can affect photosynthetic productivity and oxygen production rates. This creates coupling between atmospheric oxygen and ozone that helps stabilize both gases within ranges compatible with complex life. Ocean chemistry responds to reduced ultraviolet penetration as ozone protection enables photosynthetic organisms to survive in shallower waters, where ultraviolet intensity had previously been lethal. Marine productivity increases in near-surface environments that had been uninhabitable, creating new ecological niches for organisms that can exploit high light intensities without ultraviolet damage. This productivity increase contributes additional oxygen to atmospheric accumulation. The ozone shield forms above through photochemical processes that transform atmospheric oxygen into Earth's first comprehensive protection system against ultraviolet radiation, creating the atmospheric foundation necessary for terrestrial life while establishing regulatory mechanisms that help stabilize planetary atmospheric chemistry. Multicellular life takes its first steps in ancient seas as organisms begin the slow assembly of cellular cooperation that will define biological complexity for the rest of evolutionary time. Protected by ozone and powered by oxygen. These early multicellular experiments represent tentative departures from billions of years of single-celled existence, creating biological structures that require unprecedented coordination between individual cells. The transition from unicellular to multicellular organization becomes one of evolution's most difficult innovations, demanding solutions to problems of cellular communication, resource distribution, and collective decision-making that had never existed in single-celled organisms. The first multicellular organisms emerge as simple aggregations of identical cells that remain capable of independent survival, representing evolutionary experiments in collective living rather than true multicellular integration. These colonial organisms develop mechanisms for cellular adhesion that keep individual cells connected while maintaining the metabolic independence that characterizes unicellular life. Cell-to-cell communication remains rudimentary, operating through simple chemical signals that coordinate basic activities like movement and reproduction across cellular aggregates. Scientists studying the transition to multicellularity find evidence that early multicellular organisms evolved independently multiple times, suggesting that environmental conditions during the late Proterozoic favored collective cellular organization. The availability of atmospheric oxygen may have enabled the energy-expensive processes of intercellular coordination, while ozone protection allowed multicellular organisms to exploit shallow marine environments where single cells would have been vulnerable to ultraviolet damage. Cellular differentiation begins as some cells in multicellular aggregates specialize for specific functions that benefit the entire organism rather than individual cellular survival. Early specialization includes reproductive cells that focus exclusively on generating offspring, structural cells that provide mechanical support for multicellular bodies, and feeding cells that concentrate on nutrient acquisition and processing. This division of labor represents a fundamental departure from single-celled existence, where each cell must perform all necessary biological functions. The evolution of programmed cell death emerges as a crucial innovation that enables multicellular organisms to eliminate damaged or unnecessary cells without harming the overall organism. This represents a revolutionary concept in biological organization, individual cells sacrificing themselves for collective benefit that had no precedent in unicellular life. Programmed cell death becomes essential for multicellular development, tissue maintenance, and the complex morphological changes that characterize advanced multicellular organisms. Genetic regulation becomes more sophisticated as multicellular organisms develop mechanisms for controlling which genes are expressed in different cell types at different times during development. Early multicellular organisms evolve regulatory DNA sequences, transcription factors, and signaling pathways that enable identical genetic information to produce different cellular phenotypes. This regulatory complexity represents one of the most important innovations in the history of life, enabling single genomes to specify multiple cellular identities. Only took the availability of atmospheric oxygen and ozone protection a few tens of millions of years to enable biological innovations that had been impossible during billions of years of unicellular evolution. Only took environmental stability this brief interval to provide the foundation for multicellular experiments that would transform planetary ecosystems. Only took evolution this geological moment to begin the transition toward biological complexity that characterizes modern life. The mystery of multicellular origins puzzles evolutionary biologists who study the cellular mechanisms that enable collective organization. How did cells that had evolved for individual survival develop the cooperation necessary for multicellular integration? Perhaps oxygen availability enabled the energy investments required for intercellular communication. Perhaps environmental stresses favored organisms that could achieve larger sizes through multicellular organization. Developmental biology begins as multicellular organisms evolve mechanisms for controlling growth, morphology, and cellular organization during the transition from single fertilized cells to complex multicellular adults. Early developmental systems remain simple compared to modern embryology, but they establish the basic principles of controlled cellular division, differential gene expression, and morphological pattern formation that will characterize all subsequent multicellular life. Size advantages become apparent as multicellular organisms achieve body sizes impossible for single cells, enabling new ecological strategies that exploit size-based benefits like predator avoidance, resource competition, and habitat modification. Larger organisms can maintain internal chemical environments that differ from external conditions, creating physiological independence from environmental fluctuations. They can also consume smaller organisms and modify physical environments in ways that provide competitive advantages. Tissue organization emerges as specialized cells begin forming integrated structures that perform complex functions impossible for individual cells. Early tissues include simple epithelial layers that create barriers between internal and external environments, connective tissues that provide structural support for multicellular bodies, and contractile tissues that enable coordinated movement of entire organisms. These tissue innovations create the anatomical foundations for advanced multicellular complexity. Sexual reproduction becomes more sophisticated in multicellular organisms as specialized reproductive tissues enable more complex mating systems and genetic exchange mechanisms. Multicellular organisms can invest significant resources in reproductive structures, gamete production, and mating behaviors that would be impossible for single cells. This reproductive complexity accelerates evolution by increasing genetic recombination rates and enabling more efficient selection for beneficial traits. Sensory systems develop as multicellular organisms evolve specialized cells that can detect environmental changes and transmit information to other parts of the organism. Early sensory capabilities include simple light detection, chemical sensing, and mechanical stimuli response that enable multicellular organisms to navigate complex environments more effectively than single cells. These sensory innovations become foundations for nervous system evolution and behavioral complexity. Marine ecosystems begin changing as multicellular organisms create new ecological interactions that had no precedent in microbial communities. Predation, parasitism, and competition take on new dimensions when organisms can achieve sizes, morphologies, and capabilities impossible for single cells. These ecological innovations drive evolutionary arms races that accelerate morphological diversification and ecological complexity. The fossil record begins preserving evidence of multicellular life as organisms develop hard tissues, complex morphologies, and body sizes that can survive fossilization processes. These early fossils provide direct evidence of the transition from microbial to multicellular ecosystems, documenting the anatomical innovations that enabled complex life while preserving evidence of the ecological relationships that drove multicellular evolution. Multicellular life takes its first steps through biological innovations that enable cellular cooperation, tissue organization, and collective functions that transform simple cellular aggregates into integrated organisms capable of complexity impossible for unicellular life, establishing the foundation for all subsequent biological evolution. Earth learns to breathe through the slow establishment of atmospheric rhythms that will sustain complex life for billions of years to come, settling into the oxygen cycle that transforms a toxic waste product into the foundation of planetary metabolism. The planet that once suffocated in methane and hydrogen sulfide now inhales and exhales with the collective respiration of countless organisms. Each breath part of a global circulation that connects the smallest bacterial cell to the vast atmospheric envelope that cradles all terrestrial life. This breathing represents the culmination of the most dangerous transformation in planetary history, the near-death experience that taught Earth how to live. The atmospheric composition stabilizes around concentrations that balance the competing demands of oxygen production and consumption, creating chemical equilibrium between photosynthetic organisms that generate oxygen and aerobic organisms that consume it. This balance operates through feedback mechanisms so subtle that atmospheric oxygen concentrations vary by less than a few percent over million-year timescales. Despite the enormous biological productivity that could destabilize the system within centuries if regulatory mechanisms failed, the precision of this regulation suggests that life and atmosphere have become integrated into a single system. Ocean currents establish circulation patterns that distribute oxygenated water throughout marine environments, creating the first global oxygen delivery system that can sustain aerobic life in the deepest ocean basins. The thermohaline circulation that emerges during atmospheric stabilization operates like a planetary cardiovascular system, pumping oxygenated surface water to depths where it supports complex ecosystems that could never survive in the stagnant, oxygen-free deep waters that characterized ancient oceans. This circulation becomes the breathing apparatus of marine life. Continental surfaces begin developing the first soils as weathering processes, protected by ozone from ultraviolet sterilization, create chemical environments where organic matter can accumulate and terrestrial life can eventually establish itself. These proto-soils represent Earth's preparation for land-based ecosystems, chemical foundations that will support the root systems, nutrient cycling, and biological complexity that characterizes terrestrial life. The land learns to breathe through the slow development of soil chemistry that can exchange gases with atmospheric circulation. Seasonal rhythms emerge as the planet develops atmospheric dynamics that respond to solar radiation cycles, creating the first global weather patterns that distribute heat, moisture, and atmospheric gases according to predictable temporal patterns. These seasonal cycles become the planetary breathing that coordinates biological productivity across latitudes and through time, synchronizing reproductive cycles, migration patterns, and metabolic activities with atmospheric and climatic rhythms that operate on planetary scales. Scientists studying the transition from unstable to stable atmospheric oxygenation find evidence that Earth required hundreds of millions of years to develop the regulatory mechanisms that maintain contemporary atmospheric composition. The learning process involved multiple episodes of atmospheric instability, oxygen crashes, and recovery cycles that gradually refined the biological and geochemical systems responsible for atmospheric regulation. This learning represents evolutionary problem-solving at planetary scales. The global carbon cycle achieves new stability as oxygen-dependent processes create more efficient coupling between carbon fixation through photosynthesis and carbon release through respiration and decomposition. The ancient carbon cycle, dominated by anaerobic fermentation and burial processes, transforms into the aerobic system that maintains atmospheric carbon dioxide and oxygen concentrations within ranges compatible with complex life. This carbon cycling becomes the metabolic foundation of the breathing planet. Biological diversity begins expanding as stable atmospheric conditions enable evolutionary experiments in complex morphology, physiology, and ecology that would be impossible in unstable atmospheric environments. The availability of reliable oxygen concentrations allows organisms to invest in oxygen-dependent metabolisms, complex developmental programs, and ecological relationships that require predictable environmental conditions. Atmospheric stability becomes the foundation for biological complexity. Only took Earth's atmosphere several 100 million years to learn the regulatory mechanisms necessary to maintain stable oxygen concentrations that could support complex life for billions of years. Only took planetary evolution this geological interval to develop the integrated systems that transform atmospheric chemistry from chaotic oscillation to stable circulation. Only took life's collective innovation this extended moment to teach the planet how to breathe with the rhythm that sustains modern ecosystems. The mystery of atmospheric regulation continues to puzzle Earth system scientists who study the mechanisms that maintain planetary atmospheric composition within habitable ranges despite perturbations from volcanic activity, biological productivity changes, and external forcing from solar evolution. The regulatory mechanisms appear more sophisticated than simple negative feedback, suggesting emergent properties of planetary systems that operate through principles not yet fully understood by contemporary science. Volcanic outgassing rates adjust to the new atmospheric chemistry as the interaction between atmospheric oxygen and volcanic emissions creates equilibrium conditions that help maintain long-term atmospheric stability. The chemical reaction between volcanic gases and atmospheric oxygen produces emissions with compositions that tend to buffer atmospheric changes rather than amplify them. This geological breathing contributes to planetary atmospheric regulation. Weather systems develop complexity as oxygenated atmospheres support atmospheric chemistry and physics that create more sophisticated circulation patterns, storm systems, and climatic dynamics. The presence of atmospheric oxygen enables chemical processes in the atmosphere that affect cloud formation, precipitation chemistry, and atmospheric heat distribution. These weather systems become part of the planetary breathing apparatus that distributes atmospheric gases globally. The hydrological cycle becomes more complex as atmospheric oxygenation changes the chemistry of precipitation, surface water, and groundwater systems. Oxygen dissolved in rainwater creates new weathering processes, affects soil chemistry, and influences the biological productivity of freshwater ecosystems. The integration of atmospheric oxygen into water cycling creates additional regulatory mechanisms that help stabilize planetary atmospheric composition. Marine productivity reaches new equilibrium levels as ocean oxygenation enables more efficient nutrient cycling, supports larger and more complex organisms, and creates marine ecosystems with productivity levels that can sustainably support atmospheric oxygen concentrations. The oceans become the lungs of the planet, producing most atmospheric oxygen while consuming atmospheric carbon dioxide through biological processes that operate at scales sufficient to influence global atmospheric composition. Earth learns to breathe through the patient development of regulatory mechanisms that integrate biological, chemical, and physical processes into planetary systems capable of maintaining atmospheric composition suitable for complex life. establishing the breathing rhythms that will sustain biological evolution for the remaining history of the planet. Having survived the transformation that nearly ended life before it truly began, the ancient crisis passes into geological memory as Earth settles into the oxygen rhythm that will define all future life. Breathing slowly with the collective metabolism of countless organisms that have learned to transform poison into sustenance. The planet that once nearly died from its own innovation now pulses with the steady circulation of atmospheric gases. Each molecular exchange part of a vast respiratory system that connects every living cell to the sky above. Time moves differently now, measured not in the violent oscillations of atmospheric catastrophe, but in the patient cycles of seasons, tides, and the slow turning of continents that carry their burden of breathing life through space. The purple world of ancient bacteria fades into deep time, preserved only in chemical signatures buried in rocks that few will ever read, in the genetic memories of organisms that survived by learning to breathe the poison that killed their ancestors. The methane greenhouse that warmed this world for billions of years disperses into the cosmic background, its warming power transformed into the water vapor that rises from contemporary oceans, falls as rain on oxygenated landscapes, and nourishes the green chemistry that replaced the purple. Only the deepest refuges remember the ancient atmosphere, hidden communities of anaerobic life that still practice the metabolisms of a vanished world. Oxygen molecules continue their patient circulation through blood and sap, through soil and stone, through the respiratory systems of creatures not yet imagined, carrying the energy that enables thought, movement, and the complex chemistry of consciousness itself. Each breath drawn by future organisms will depend on this ancient catastrophe, on the near extinction that taught Earth how to sustain the biological complexity that makes such breathing possible. The poison has become the foundation. The waste product has become the necessity. The crisis has become the gift that enables all subsequent life. Stars wheel overhead in patterns that will shift through geological time, while the atmosphere below maintains its oxygen concentration with the precision of a planetary heartbeat. Neither too much nor too little. Regulated by mechanisms so subtle they seem like cosmic accident, but represent the patient work of evolution solving problems at planetary scales. The breathing never stops, never falters, continues through ice ages and warm periods, through extinction events and evolutionary radiations, through the rise and fall of countless species that depend on atmospheric stability for their brief existence. The Earth breathes on. Having learned through crisis the rhythms that sustain worlds, carrying its cargo of oxygen-dependent life through the vast silence of space where other planets wait, perhaps for their own atmospheric transformations, their own near-death experiences that might teach them, too, how to breathe. Sleep comes to worlds as it comes to organisms, a settling into rhythms larger than individual awareness, a surrendering to cycles that connect each moment to the vast span of geological time. Rest well in the knowledge that the air you breathe carries the memory of ancient crisis, the gift of organisms that died so that breath itself could become possible. The oxygen crisis passes into dreams of deep time, where purple seas remember methane skies, and the first breath echoes through eternity.